Chapter 13, Gravitation. Section 1 is looking at Newton's law of gravitation. So this gravitational force holds us to the Earth, holds the Earth in orbit around the Sun, holds the Sun together with the stars in our galaxy, reaches out across intergalactic space to hold together the local group of galaxies, holds together the local supercluster of galaxies, pulls the supercluster toward the great attractor, attempts to slow the expansion of the universe, and is responsible for black holes. In other words, gravity is quite far-reaching and very important. And now we get to take a closer look at what gravity actually is, besides the fact that it's just always there and always trying to bring us down. So this gravitational attraction will depend on the amount of stuff an object is made of. Earth has a lot of stuff, mass, right? And so it produces a very large attraction. Interestingly, this force is always attractive. It's never a repulsive force. So it's always pulling closer. There isn't a way to make it repel. Gravitation is the formal term for the tendency of bodies to attract one another. And Newton realized this attraction was responsible for maintaining the orbits of celestial bodies, of planets, of stars, and the like. And so Newton's law of gravitation defines the strength of this attractive force between particles, like between the apple and the Earth, which we'll come back to in a moment. But let's take a look at mathematically what Newton's law of gravitation is. So the magnitude of this gravitational force is given by the force is equal to big G times m1 times m2 divided by r squared, where big G is the gravitational constant. This is a universal constant for anywhere in the universe, right? It's not just on Earth. This applies if you are near Jupiter, if you're anywhere else, and it's always equal to 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. So that's the constant. Then we have m1 and m2, which are the two masses that are involved in this. And then r is the distance between those two masses. And those two masses, which are often treated as two particles, it's going to be an attractive force between them. And so the force will always point from one to the other because they're always drawn to the opposite one. And so we could write this equation in vector form where we have the same magnitude out in front, but it's times r hat, which is just in the direction of the radial connection point between them. And we can demonstrate this, draw this out where we have these two particles, particles 1 and 2, and particle 1 feels a force that's going directly towards particle 2. So we draw the vector with the tail on particle 1 to show that it is being pulled towards particle 2. We don't draw it as pushing, it's always pulling. And the unit vector r isn't the full magnitude of the force, it's just the direction. It's just saying, hey, this is the radial direction. This is how we get from particle 1 to particle 2. So r hat's a useful construction. It could break down to purely x hat, like if the two particles are on the x-axis, if they're just in a flat line, then r hat will just be in that horizontal direction. All right, now getting back to our apple and the Earth. Newton's law of gravitation, if you plug in the numbers, we find that the attractive force of the apple to the Earth is about 1 Newton, which is very convenient. So now you know what 1 Newton is it's about an apple in terms of how that feels. Now what about for two people? What's the attractive force between any two people? So try to estimate a value for this attractive force, and there's a conversion there of kilograms to pounds. So I encourage you to pause and think about this. What would some reasonable numbers be? See if you can get an answer. So go ahead and hit pause now. Okay, did you do that? I hope so. Well, you can check with, I went ahead and tried it out with the average weight of an American woman and man. And the average apparent weight of an American woman is 160 pounds and of a man is about 190 pounds. So if we plug those things in, with our universal gravitational constant, 6.67 times 10 to the negative 11, 160 pounds converted to kilograms, or 1 kilogram divided by 2.205 pounds, times the other mass, 190 pounds, but again converted to kilograms, and divided by, I said a distance of 1 meter, just to keep it convenient. This is not social distancing, so please be aware, if this was a socially distanced setup, we would have to do 2 meters here. But 1 meter squared is easier to calculate. And so with those numbers, I got 4 times 10 to the minus 7 newtons. This is a tiny amount of force, right? This is less than half of a micronewton. But there's potentially some lessons to be learned here, right? You can learn, how can we increase this attractive force between two people? Well, one is we could increase their masses. If people become more massive, they're now more attractive to each other. So that's something you could try. Not accepting any responsibility for this. Also, it's divided by the distance squared. That means any changes to the distance between those two people is going to make a really big difference on the overall force felt. So we did it with 1 meter, but if you get really close, you might be even more attractive, at least in terms of Newton's laws. I'm not sure if it works in terms of other attractiveness. So keep that in mind, but that's a demonstration of Newton's law of gravitation applied to two people. And it's actually good that this is a weak force, because otherwise we would be walking down the street and they would just be like, oh, and we'd feel this attractive force pulling us side to side if there is a wall, because a wall had mass, if there's anything. So it's really good that it only really pulls on us with very massive objects like the Earth. And it turns out the gravitational force does form these third law force pairs. So the Earth apple and apple Earth, there's both a force there. The apple feels a force from the Earth does feel a force from the apple. And they're both about 1 Newton, 0.8. But we see the apple fall, and fortunately we do not see the Earth suddenly bounce off in a random direction because someone happened to drop an apple. The key is that even though the force is the same, there's a very big difference in mass. And so there's a huge difference in their accelerations. So the apple is able to accelerate at about 10 meters per second squared, or 9.8 to be more exact. But the Earth, because it's so massive, if you remember F equals ma, if you have that same force but divide by a huge amount of mass, the acceleration is now 10 to the minus 25 meters per second squared. So that's minuscule. All right, one more lesson here is the shell theorem. This describes gravitational attraction for objects. It says that a uniform spherical shell of matter attracts a particle that is outside the shell as if all the shell's mass were concentrated at the center. And we can use this with Earth. We can treat Earth as a nesting of shells, right, where you're just adding another shell, and each of those shells, all the mass of that shell is just concentrated at the center. So it allows us to treat the Earth like a point particle instead of a huge, spacious planet. Let's test this out with a checkpoint. Particle is to be placed in turn outside 4 objects, each of mass m. 1, a large uniform solid sphere. 2, a large uniform spherical shell. 3, small uniform solid sphere. 4, small uniform shell. In each situation, the distance between the particle and the center of the object is d. Rank the objects according to the magnitude of the gravitational force they exert on the particle, greatest first. Right? I want you to think about this, settle on an answer, so please go ahead and press pause now. Okay, trusting you did that. Now let's take a look at this. As in the descriptions, they have these different sizes and even different mass distributions. But the key here is that each of them, regardless of their shape or size, is of the same mass m and the same distance between the particle and the center of the object, right? So even if you have a really massive shell or a really small one, if it's the same distance from the center to the object of interest, based on the shell theorem, either of these will have the same result as long as that distance is the same and the total mass is the same. What does this mean? Well, the small one is going to have to be probably much denser than the big one in order to have the same amount of mass with that much smaller volume or shell. But as long as it does have that same mass and the same distance from our point of interest, it is going to be equal forces from each of those on the particle. All right, that brings us through the end of section 13.1, Newton's law of gravitation.